again. Indeed. And our guest today is Wolfgang Wieland from Erlangen, who is going to tell us about, well, no surfaces and muon elements. May I actually sit here?
Yes.
No, that's fine.
Thank you, Jerzy, for the introduction, and I would also like to thank Wojtek for the invitation and the Poisson Institute for the hospitality here also. So I will speak about, so usually when I speak about this null surface program, I really want to see this as a program towards quantum gravity. But here I want to, I'm considering a much simpler case. So for instance, when in September, when I was here for the conference, I was speaking about gravitational null emission data. This is just about U1 electrodynamics. And this is with a master student at Friedrich Alexander University, Erlangen, and everything is funded by the German research society. So instead of in loop quantum gravity, we use SU2 spin network states to construct quantum states of geometry. These states are built by Wilson line operators for the Ashtekar connection. As a toy model, one often considers a much simpler theory where one just puts electrodynamics on the lattice. So instead of spin network states, we work in this context just with so-called charge network states. And first of all, I will just briefly review that. And then this charge network representation is based on the phase space on a space-like Cauchy surface, a space-like initial surface. And then in the first new step is to take this to null initial surfaces and look at local subsystems on subsystems on null initial surfaces. And then we ask ourselves, well, just like on a spatial hypersurface, we have a charge network representation. Can we quantize the resulting holonomy algebra? And there will be a few things that are markedly different from this space-like case. But let's first consider that just to put everything on equal stage, the charge network representation of the quantum Maxwell field. This is a sort of lattice representation of QED. Just like we can put QCD on a lattice, we can also do this with quantum electrodynamics. So the starting point is just the action for electromagnetism, so for U1 gauge field in a fixed background spacetime. FAB is the field strength of the vector potential. This prefix, so AB are four-dimensional abstract spacetime indices. This prefix 4 that appears all the time, it should just remind ourselves that we are considering fields in the bulk. And when we take the pullback to the boundary, I will drop this prefix. So now, how do we get the phase space from the action? Well, one way to do that is to look at the Hamilton principal functional, at the Hamilton-Jacobi functional. If you evaluate the action on shell, the variation of the on shell action. So if you plug in the equations of motion, then the variation of the action for fixed boundary conditions gives you the momentum conjugate. So the boundary term tells you that the momentum conjugate to the vector potential is the pullback to the boundary of the Hodge dual of the Faraday tensor. In other words, you can infer from this boundary term the symplectic potential, the symplectic current, and these boldface D's in here, they are just to distinguish exterior derivatives on spacetime from exterior derivatives of phase space. These boldface double stroke D's are variations or differentials, exterior derivatives on phase space. So this term tells us that the momentum conjugate to the vector potential is the Hodge dual of the field strength. And now if we evaluate this on a spacelike hypersurface, so we take the integral of this current over a spacelike hypersurface, we get the familiar thing. The Poisson brackets tell us on sigma that the electric field, which is a densitized 3-vector on sigma, is canonically conjugate to the vector potential, and HAB here is the projector onto sigma. And this is a kinematical phase space, so there is a constraint. In the case of electromagnetism, there's only one constraint, namely that the electric field is divergence free. And then if we now we want to quantize this phase space, but not using standard covariant methods, but like lattice methods, like in Lucas gravity. So what we do is we quantize a different algebra, an algebra of smeared variables. So we smear the electric field over two-dimensional surfaces, and the vector potential we smear over one-dimensional paths, obtaining the holonomy. So if this is a closed path, this is just the exponential of the magnetic flux, and this is just the electric fluxes. So this is why I say compactified magnetic fluxes, because we take the exponential. So a phase, everything is modulo 2 pi. And then the Poisson brackets of the continuum theory imply commutation relations of the smeared variables. These commutation relations are very simple. We get a non-vanishing, so epsilon that this epsilon that depends on the surface and the path is non-vanishing if and only if there's an intersection of the path gamma with the surface delta, and it's plus or minus 1 depending on the relative orientation between the surface and the path. And then we can restrict ourselves to a fixed graph, so just a collection of such paths. For instance, a graph dual to a triangulation, and we can quantize them very easily just by saying that the holonomies act as shift operators, whereas the electric fluxes just count these flux quantum numbers. This is essentially the quantization of T star of U1 to the number of paths in the graph. And the Gauss constraint then tells us that these quantum numbers cannot be arbitrary. Whenever these paths meet at the vertex, the charge quantum numbers must sum up to 0. This is just the vanishing of the total electric field. So if you have a closed surface where there are a number of paths coming in or coming out, each of them carries some quantum numbers n1, n2, n3, and so on. The total number of these charges, these quantum numbers n1 to n, how many intersections there are with the surface, should sum up to 0. This is the abelian version of the Gauss law, and in a lattice gauge theory, and generally in Lucas gravity, we have a non-abelian version of that. And that, yes?
Question, because something worries me here.
Yes.
I'm sorry, because it's fundamental question.
Yeah.
So, the second action of the electrical flux operator, right?
Yes.
You have this intersection number, which seems to be quite odd, because you would expect that if you find the representation theory, then somehow you should forget about the whole of classical geometry. This essentially tells you something about the geometry of the particle geometry.
That's because this algebra is not background invariant. So there is not a topological field theory, because there is electromagnetism in 4 space-time dimensions on a fixed metric background, and this background is not dynamic here. And then it's not so surprising that the Poisson brackets know about the metric. So this is different from a topological field theory. And now the way I presented things here, everything depends on this graph. So Ashtik and Lewandowski actually found a way to take the continuum limit to allow arbitrary graphs, and then one can understand the resulting Hilbert space or the Hilbert space inner product as an ordinary L2 space over the space of generalized connections. And now so this is in a nutshell the quantization of electrodynamics on a lattice. And one can do lattice QED in this way. This is always very standard. But now we can ask ourselves, what happens if this hypersurface is not spacelike but null? What do we get instead? And we will see that we get something quite different, in fact. So the starting point is just has nothing to do with the quantum theory. We just look at the classical covariant phase space of subsystems on null initial surfaces. The same that we want to do in gravity, but now in a simplified setting where we just look at electromagnetism. The advantage of working with null surfaces is that they have more structure. So we can picture them, if we exclude caustics, just as fiber bundles, where the fibers that lie tangential to these hypersurfaces are just the light rays. And there's a natural projection onto the base manifold, which is the projection along the null rays onto a two-dimensional cut of this three-dimensional hypersurface. And now we want to put electromagnetism on this hypersurface or the phase space of electromagnetism on the hypersurface. And at that point, it is just very useful to introduce a Newman-Penrose tetrad. So we diagonalize the metric. Remember that we are not restricting ourselves to a specific class of light cones or a specific null sheets or a specific background metric. This may be a null surface in any curved geometry. And now we introduce a Newman-Penrose tetrad that diagonalizes the four-dimensional metric tensor. To do that, we need four covectors, L, K, M, and M bar. M and M bar are complex, and the L and K are null vectors. And what we choose such a Newman-Penrose tetrad that is actually adapted to this null hypersurface. By that we mean simply that this tetrad exists in a neighborhood of the null hypersurface, and both K and L should be surface orthogonal. And furthermore, L should be the normal vector to the null hypersurface itself. This is to say that the pullback of this, that L is the normal vector to N. In other words, that the pullback of this one form to N vanishes. And the pullback of the other two covectors just defines some co-basis on the null initial surface. And then we need to do, so later on we will compute also look at the Faraday tensor, so we need to take exterior derivatives. For that reason, it is useful to take exterior derivatives of this covectors. So this is for a generic null hypersurface, this will be an unholonomic basis. So the exterior derivatives of M and M bar will actually be non-vanishing. The coefficients that appear in the expansion, so if you take this two form and expand it in the basis vectors, have a simple geometric interpretation. These components are the expansion of K and L, and these other components define the shear of the two null directions, L and K. And gamma plays the role of a U1 spin connection that gauges the freedom that we have in here to rotate M and M bar by a U1 phase. Furthermore, we have restricted ourselves to a double null foliation. So K, we can say it's just the gradient of some potential, and L then will also be surface orthogonal, so satisfy this Frobenius condition.
And the infinity, what is it?
The infinity just means that the vector, so with this choice, the null vector LA is not affinely parametrized. So we have an equation that B nabla B is not zero. So if both L and K are surface orthogonal and no, in here in this Newman-Penrose formalism, they're always normalized to satisfy to one, that the two null directions have a specific normalization, and then you can always choose one to be affinely parametrized, but not both of them simultaneously. That's why there is this non-affinity. Okay, and now we go. Now we need now we compute in these variables the electric and magnetic fields, because we need to know them to compute the symplectic potential. And for that, we first split the vector potential in the neighborhood of n into these bases. And then we can always make a gauge choice that one of the basis components is just a gradient. So up to a gauge transformation, so we can always write it in that form. Okay, and then we have this expression and we compute the Faraday tensor and its pullback to the and the dual Faraday tensor and its pullback to the null hypersurface. And now there is already something important to observe, because so what do you see here? So in the magnetic fields, our basis on the null hypersurface in the space of two forms is m wedge m bar and k wedge m bar and k wedge m. And here you see in the magnetic fields and in the electric part of the field strength tensor, essentially the same expression appearing, just with a relative I, right? And the fact why this appears is just because and this is very different from a spacelike hypersurface, that on a null hypersurface there are self-dual two forms. So the Hodge dual of K, remember K is just du, so du wedge m. This two form is self-dual, so it's Hodge dual reproduces itself up to a factor of the imaginary unit. And then now these two forms appear both in the decomposition of the Faraday tensor and its dual on the null hypersurface. And so what we see here is that electric and magnetic fields on the null hypersurface are no longer functionally independent. This is very different from a spacelike hypersurface. Remember, on a spacelike hypersurface, B is odd A, and E is gradient phi minus A dot. So to get the electric field, you need to know the time derivative of the magnetic field of the hypersurface, while for the magnetic field, you just need the vector potential. While for the electric field, you need to know the time derivative of the vector potential. On the null hypersurface, the time direction or the normal direction becomes tangential to the hypersurface, which is why the two are no longer really independent. And that's what you see here, that these two form, one is just the other multiplied by an imaginary unit. So electric and magnetic fields are no longer functionally independent. And that means, and from that alone, one can in fact already expect that the vector potential no longer commutes with itself. So we expect that holonomies no longer commute among themselves, and we will see how this will work out. But now let's go on. So the symplectic potential on the null hypersurface just looks like this. It's just the same expression as for the spatial hypersurface, just that we take the integral over the null boundary. Then we insert our parameterization of the vector potential in terms of these components, in terms of the m and m bar components and this gradient lambda, the gauge transformation. And we insert this expression up into here, and we get three terms. the first term only depends on alpha and alpha bar, and this lambda, the gauge parameter, will only appear in these corner terms that appear because the null hypersurface has two cuts. So there's an initial and final cut, and then the gauge parameter lambda will show up as a so-called edge mode at the boundary of this null strip. And the expressions are as follows. So in the radiative symplectic potential, we have the time derivative of alpha, one of the components of the vector potential along the null direction, and then some other expressions involving the shear of the null surface, the expansion, and the rotational connection, U1 connection. And similarly, there's an edge mode contribution that tells you that the gauge parameter is canonically conjugate to the electric field at this two-dimensional cut.
So what is the calligraphic C?
Calligraphic C is a cut, a two-dimensional cut of the null surface. The null, I'm considering not an infinitely extended null hypersurface, but a null hypersurface that is just a strip. So it has an initial boundary and the final boundary.
Okay,
and then
so the C has two parts.
So there's a C plus and a C minus, and the expression for C plus minus is the same, looks the same integral, same type of integral evaluated at two different 2D cuts. And we won't consider this corner contribution in what follows. We are only interested in the null symplectic structure along the strip. And now this shear term looks a bit more complicated. However, if we now take to compute Poisson brackets, we take the exterior derivative on phase space of the symplectic potential. So the D of this expression. And then the shear term goes with alpha bar, but the exterior derivative of that term with the exterior derivative of alpha bar gives 0. So the shear term falls out of the symplectic 2 form that we calculate from the exterior derivative of theta. So we only get these 3 terms, and that really simplifies now the calculation. Because now we can basically just integrate that. So to integrate that, we introduce a conformal factor. So actually, I don't really have to go through these details here, but the metric at the null boundary can be expressed in terms of these dyadic one forms, and these can be parameterized by an over conformal factor and some SN2R matrix. And in the expansion, for instance, is just omega minus 1 time derivative of omega, and this phi can as well be written as the time derivative of some U1 holonomy. I've written it here. So we write the expansion as omega minus 1 d by du omega. D by du is just a null vector along this intrinsic to the null hypersurface along this null race. So there's a clock variable, and the 2 cuts, C plus minus, are at boundary values plus minus 1. And then there's also U1 holonomy, which is just this U1 frame rotation along the null race. And now we can simplify this expression for the symplectic 2 form. LL is the derivative along the null direction, just as an ordinary partial derivative of this dressed expression, where we dress the component of the vector potential by this U1 derivative and the conformal factor. And now this symplectic, remember we work in a fixed space-time, so omega and this U1 holonomy are just fixed, so we can pull them into this exterior derivative by just performing a change of variables. And then it's easy to compute the resulting Poisson brackets between alpha and alpha bar. They're just a step function, then inverse of the conformal factor and some phase. And in the angular directions, we just get a two-dimensional theta function. And there is also another way to do this calculation more explicit, just doing a mode expansion along this one-dimensional strip. And then you end up with essentially infinitely many, and then a mode expansion in this coordinate. And but this interval is compact, so rather than a Fourier transform, we have a Fourier series rather than a Fourier integral. We have a Fourier series, and actually it is useful to split this into. By doing this mode expansion, you have to choose some boundary conditions. Usually, and if you want to relax these boundary conditions, we can do that by just adding what I call a soft part, which grows linearly along the null direction. And then what you get are infinitely many harmonic oscillators and one additional mode that for these soft modes. That is basically the zero mode of these oscillators, which is not included in these Poisson brackets, shifted by some boundary term. And if you use this Poisson bracket, you can argue that you can find that in a distributional sense, you obtain these Poisson brackets for the modes. Okay, so now we have alpha and alpha bar are components of the vector potential. And now we know there are Poisson brackets on this null strip. So now it should be possible to look at the holonomy algebra. So what types, and in the following, I restrict myself to a certain class of holonomies, namely that remember this null hypersurface has two cross sections, an initial cross section and a final cross section. And in what follows, I restrict myself to a specific class of parts, which we call hoops, because they look like a hoop. So they go some time, they consist of three parts. One goes from the initial cut along a null direction to a point in the interior of N, and then along a spacelike path, and then back along a null ray to the initial cut. And we now consider the Wilson line operator along this hoop, and up to a gauge transformation, it is just the integral of this alpha bar terms along this space-like segments, which I call gamma hat. And gamma check is then the projection onto the initial cut. And now notice that in this Wilson line, only alpha and alpha bar appear. However, we know also there are Poisson brackets. So now we can just insert this expression into the Poisson brackets and compute the algebra of Poisson brackets between two such hoops. And from the structure of the Poisson brackets, it's clear that there will be no contribution, that there will be that Wilson lines commute unless they intersect the same light ray, because the angular coordinates are the same along each, so each light ray is coordinatized by the same angular coordinates, but there's a delta function in here. So this can only have non-trivial contributions if we are at the same light ray, which I've indicated in here. So these Wilson lines are non-commuting only if they intersect the same light ray, or in other words, if the projection onto C minus intersects. And to do the calculation now, this is the homework for the student, you smear these lines into one-dimensional strips, and then do the Poisson bracket, and the only contribution from the Poisson bracket is then a two-dimensional plaquette. And since you have a delta function in the Poisson bracket, this then has a finite integral. So you just get a number. For vanishing shear, the algebra is very simple. So you get the Poisson algebra between two holonomies, gives again two holonomies times some function. And this function depends on the cosine of the angle at the intersection, so this angle, and divided by the norm of the sine. That there is the norm of the sine. This is just the absolute value just comes from a coordinate transformation. It's a sort of Jacobian, going from one, because you use adapted coordinates where these tangent vectors are the coordinate lines. And then for non-vanishing shear, the algebra looks a bit more complicated. So you have again the same structure. So holonomy gives holonomy times holonomy. And then this is stressed by some expression that depends on the path-ordered exponential of the shear between these 2 points, basically, from here to there. And this check plus minus is just the tangent vector of these paths pushed forward under this map pi onto this initial surface. So for non-vanishing shear, these Poisson brackets know about the integral of the shear. In a sense, the integral of the shear asymptotically is what we would call gravitational memory. And notice this structure, holonomy, product of holonomies, something, this appears all the time in the algebra of null hypersurfaces. Even for the gravitational case, you get a similar algebra, but now the expressions look a bit more complicated. This just as a side remark. Now we want to, now we have Poisson algebras between U1 holonomies. On a spacelike hypersurface, we have this nice charge network representation. But now holonomies are non-commutative. So one has to ask: can we still quantize this algebra? So one answer would be, well, we now have this canonical coordinate, which are so one. Maybe just turn it down. Someone having a shower.
Look, maybe plug out from the microphone and plug it.
È spinto. Mi sa che è spinto.
So one could say, well, we could stop here, because here we have just harmonic oscillators and some additional Poisson brackets for these zero modes, and one should just quantize these like a Fock space. But we want to do something else, because we have these composite fields, and ask: is there just where we quantize directly these spaces, a bit like what we do in lattice QCD or in lattice electrodynamics. And now yeah. All right, thanks. Right. Sorry. Okay. So classically, we have just like before. Let's restrict ourselves to just n such hoops. Okay. So then we have Poisson brackets between two of these paths, and the structure of the algebra is as follows. So we have Poisson brackets between two U1 holonomies, and they give again a product of holonomies times some times the coupling constant and some structure constants. And these structure constants depend on the geometry at the intersection. And note that this becomes obvious in the shear-free case that if we send these two paths into each other, so if we send gamma plus to gamma minus, this becomes singular because this blows up this sign. And okay, but now we can ask ourselves, okay, how would we quantize this in the most naive way? Well, on the left-hand side, we can replace Poisson brackets with commutators, and on the right-hand side, we have a product. But this equation tells us that the holonomies don't really commute among each other. So we have to choose an ordering between these two. For instance, just a symmetric ordering. But if you think about this expression for a moment, it's just the same as to say that the product of two holonomies is the same as the inversely oriented product of holonomies times some phase. Okay, because these two on the left-hand side, you get the same, just with the minus, but a real number. Here you have only an imaginary number, and the ratio of the two combined to just the phase. And now this, however, is regular as we send one of these paths into the other ones. In fact, you get a relative minus sign. So in a sense, you can now say, well, these holonomies become anti-commuting, like fermions. And this is not so, okay, this sounds a bit crazy at first, but it's actually not that, so there is something like this happening in CFTs. So this symplectic structure is actually the same as for a CFT. And if you take the exponential of a bosonic exponential of a boson, then its 2-point functions in the CFT behave like a fermion. This is called fermionization. But the holonomy is just the exponential of alpha bar. So in that sense, it's maybe not that surprising that you get fermionic behavior. But then on top of that, we have reality conditions. So at the classical level, the holonomy is just a phase, which means that the holonomy with its complex conjugate gives 1. Now we have to represent this at the quantum level. The easiest way is to just say that that we use here a symmetric ordering, and then on the right-hand side get the identity. And if you now combine these algebraic relations with those ones, you can summarize them as follows. And where you also take into account that h bar gamma should be just h gamma to the -1. And well, for a single such path, you can now easily quantize this using fermionic oscillator representation, where each holonomy acts either as a creation or annihilation operator on some states that flip into each other under orientational reversal. This is the quantization of just one of these holonomies, if you have many of them, what you need to choose is a vacuum state that is essentially a choice of orientation for each of these paths. So we call this a training. And then one kind of difficult step is what happens under path refinements. So what happens if you split paths into two? For instance, you can say take two paths that combine to a third one. Then at the classical level, the holonomies satisfy this condition that the holonomy along the connected path is just a product of two holonomies. At the quantum level, we can impose this as a constraint on an extended Hilbert space. So this is the way we will do in this representation the path refinements that are really an important concept in Jurek's and Abai's proof of the existence of the continuum limit.
So
the whole construct, yes,
The capital N is the number of
is the number
of edges.
of edges. Yes, exactly. N is the number of edges. Yeah, why? Yeah. Yes. Thanks.
So capital K should be
N.
N.
Yes. Thanks. Yes. Correct. Okay, that's it. So, what's the take-home message? On a nice surface, Wilson lines no longer commute under the Poisson bracket, and this is a direct consequence of the fact that there are self-dual two forms on null hypersurface. Null hypersurfaces that k wedge m, its Hodge dual is just I times k wedge m. And this implies that on a null hypersurface, electric and magnetic fields are no longer independent functionally. And the basis of the standard charge network representation of loop quantum gravity is that you can use a sort of connection representation. And this connection representation is based on the fact that the connection, that all holonomies commute among themselves, that they form a commuting subalgebra. This is no longer possible on a null hypersurface, because Wilson lines that intersect the same light ray no longer commute. Then we ask ourselves, is it possible to quantize this algebra for a fixed number of paths? And we developed a proposal for such a quantization in which each holonomy becomes an anti-commuting number. And in this quantization, there's no preferred vacuum state anymore. The vacuum state depends on a choice of framing, which is an assignment of an orientation to each of these paths. And I conclude with that. Thank you.
Thank you very much. Questions now? Are there any questions from people online?
So the last part we talked about reality conditions.
Yes.
I know that, for example, in good quantum reality, sort of big reason why complex astral connections were not no longer used because these sort of reality conditions are imposed. But it seems that in your model they're not that hard to make. So
that's correct. Yeah.
Because the model is particularly simple, or there is a
yes, it's basically that. But the model is really simple. However, so in the original literature on this complex approach to loop quantum gravity, it was always conjectured that the reality conditions will determine the measure in a product on Hilbert space, and this is exactly what's happening here, because to compute the norm of your basis states, or to compute the inner product, you actually need exactly relationships of that sort. So in that sense, the reality conditions here, yes, they are very simple, but they play exactly the same role that was expected that they would play, namely determining inner product.
So I'm surprised that your theory has a fermionic character. I mean,
Yes.
well, it is well known how to quantize the Maxwell equation. You also on a curved space time.
Yes.
And you get the bosonic theory.
Yes.
And on top of if you fix a lattice, or I mean a network, then you probably get some viral algebra for canonical commutation relations. So nothing fermionic. So why you get something different?
So the reason is that as I tried to highlight here, that the holonomies themselves no longer commute.
Well, yeah, well, that's I mean, bosons don't commute either. So,
and the reason is that these are commutation relations between. These are not equal time commutation relations, because you evaluate fields at points where they are connected by a light ray. So in a sense, one way I understand is that I'm not saying that this is what one should do to quantize electrodynamics on a null hypersurface. I'm just asking a very simple question. If we were to repeat whatever we did for the spin network representation on a null hypersurface, how far could we get? And then you are forced into this different algebraic structure. It may be too small.
Yeah, but this should be equivalent to the conventional quantization of the Maxwell equation, shouldn't it? I mean,
Yeah, that's true, but I think that it's not really very strange that given, so if you start with the standard folk representation of quantum electrodynamics, you may produce some complicated operators that actually don't commute.
Yeah, but they don't commute in the standard framework either.
That's
yeah,
right.
exactly. So expression of these operators in terms of the standard state, standard creation annihilation operator of electromagnetic field is non-local and extremely complicated. So it's not really that strange that such complicated.
So you're saying that the fermionization naturally arises if you
restrict yourself to a null.
Yeah. So another question.
And just to interrupt, because there's that's something I briefly mentioned, that something similar happens in CFTs. If you take a boson, then the exponential of a boson defines a composite operator that has then different two-point functions.
Yeah. Yes.
And this is and the holonomy is just the exponential of the boson.
Yeah, but the exponential of, I mean, you have to do something. You have to fix appropriate coefficients to get exact fermionic anti-commuting. So I have a second question. So this was just a free Maxwell equation.
Yes.
Now the next step in complication, which is still linear, you can add conserved current.
Yes.
So this would it work? I mean,
I do not know.
You don't know.
No, I've not looked at it. But another step in increasing the difficulty is looking at the, which I find also interesting, is to ask what happens if we make these fields non-abelian, because then then I will get the same. So simple arguments tell you that you will get the same algebra, but these are now matrices, and you have to kind of split them where the intersection happens. So you get a richer algebraic structure, and would be quite interesting to see whether there's a connection to quantum groups, for instance, which is also a phase space on because what this is symplectic space or phase space where the basic variables are group valued. And it would be interesting to have to look at the non-abelian case where these become then non-abelian.
Well, yeah, then this is a non-linear difficult theory. So,
Yeah. But we can QCD the kinematical phase space. The kinematical we know how to quantize QCD on the lattice.
Okay, okay. So what I'm asking with the external current is much simpler and sort of well understood. Non-perturbed.
Thanks for this.
Okay.
So, as you mentioned, there was some kind of CFT-like structure that would merge, right? And I wonder if that's somehow related to the fact that you don't really have a length notion on the null hypersurface.
Exactly. Yeah.
Okay.
Yes. The entire the Poisson brackets that you get, these Poisson brackets, or also for the general case, they depend not on the metric at the boundary, but only the conformal class of the metric at the boundary. So yeah.
That's also why the answer to R thing appears.
This is a different story. Yeah, but
even when you introduce this omega right, and then say you have a set to R.
This SL2R had
But the gravity case.
this encodes really gravity degrees of freedom, the gravitation. Yes.
Perfect.
At the end, it's a summary of algebraic relations in the quantum algebra of Holonomy. Yes. So those relations look like really simple. So does this algebra have any name that's like sweeping the order is equivalent to giving phase?
Yeah, it is a.
So is this algebra well understood somehow, or
Yeah, it is a deformed. I think they call it a Q-deformed.
Q-deformed
commutative. Yeah.
It is related to quantum groups?
Usually, yes. Usually, that's what people.
Yeah.
Indeed, yes.
It's like a deformed harmonic oscillator. So you can have a dagger. Imagine you have creation and annihilation operators A and A dagger, and they can be bosonic or fermionic, but you can have commutation relations that depend actually on a phase, and that's what's happening here. That's continuously interpolated.
Any more questions? Okay. If not, thank you. Thanks to